All right, so now we've been talking about whether these series converge or not. So another interesting question is going to be, to what value do they converge? So we have ways of estimating or sometimes limiting or bounding the error. So these errors that we have, we call them remainders. You'll see why. And our first one is going to be the remainder estimate that goes with the integral test that you just learned. So the remainder estimate for the integral test. So we're going to come back to our favorite series here, the sum from n equals 1 to infinity of 1 over n squared. That series, we know it converges because it's a p series with p equals 2, which is greater than 1. All right, so that's one thing you can say about it. You don't even have to do any work. Right? If I had sum from n equals 1 to infinity of 1 over n cubed, I would say that's a p series, and it converges because it's a p series with p greater than 1. It's going to converge. All right, but what does it converge to? What is its value? What is the value of that sum? I'll write this word so you can read it. All right, so we've already seen a little bit of a hint as to how we can get a handle on it using essentially Riemann sums. So I've drawn a little graph here. It's out of proportion, between the y and the x-axis are scaled differently because this first part is really a square, of course, because it's 1 by 1, because 1 over 1 squared is 1. So if we look at a right-hand sum, then what we have already observed is that this is 1/4, this is 1, this is 1/4, this is 1/9, this is 1/16 in terms of their areas, because the bases are all 1 and the height is whatever we evaluate that function at, and it's 1 over x squared, so 1/16, etc. Okay, so so things that I can observe then is, then we also know that the integral from 1 to infinity, all right, the integral from 1 to infinity of 1 over x squared dx, we've already shown a number of times is equal to 1. All right, so this whole area, all of this is equal to 1. And we know that the 1/4 plus 1/9, all that stuff is going to be less than that. So what I have is 1 plus a bunch of stuff that is less than 1. All right, so I know, I'll just say a bunch of stuff that is less than 1. All right, so what we know to start with is that just from this diagram, we know that the sum from n equals 1 to infinity of 1 over n squared is less than 2, right? But we already, so that's what we already talked about. And if we look at some of the values we calculated, so we calculated, here's where we calculated the sum from 1 to 10. It was 1.549. Here's the sum from 1 to 100 is 1.6349. 1 to 1,000 is 1.64393457. And so words can keep going like that. In fact, I forgot to tell you guys last time that I also did the sum to 10,000. That's the one that really took the time. And we got 1.6448. So we can see this is coming to 1.644 something, right? But how close are we? We're still seeing changes in the 1,000ths place between the sum from 1 to 1,000 and the sum to 10,000. So we've done a lot, we've summed up a lot of values, and our result is still changing noticeably. So how close are we when we take 10,000 or 1,000 terms? How close are we to actually finding the value of the sum? That's what we want to be asking ourselves. So, and we can get a pretty good handle on that. So what we're going to do is we're going to look at actually any, I guess let's get some terminology, and we'll look at any positive continuous decreasing series. All right, so first of all, let's just get some little bit simplified terminology. So we have the sum from I equals 1 to n of a sub I. All right, so that's just the sum of the first n terms. All right, so that's s sub n. We call it the nth partial sum. All right, and this is the shorthand we're going to use for that. And then with the other thing we're interested in, the sum from n equals 1 to infinity. We could use I here as well, but the only reason I used I here is because I was using n up there, and now we don't have n up there, so we use whatever letter we want there. And we're going to call this just s, and we're going to call it the sum, all right? So if we sum up everything in a series, we call it the sum. If we sum up only n values, we call it the partial sum. The sum, we're going to just call it s. The partial sum, we're going to call it s sub n. Then we're going to talk about the remainder. And so what this means is, how close do we get by estimating with n terms. So when I add up 10,000 values, how close am I to the true sum? So that remainder, we call it R sub n, all right, the sum using n terms. So what it is the absolute value of the difference between these two, s minus s sub n, right? And as long as we have a positive series, so all the terms are positive, this equals s, just s minus s sub n, if all a sub n are greater than 0, right? Because the total sum is going to be larger than any of the partial sums because we're always adding on more. As long as what we're adding on is always positive, which it won't always be, but for now we're always adding positive numbers, so that remainder is s minus s sub n, all right? And so what that equals, if you think about, if s is all of the terms and s sub n is the first n terms. So if I take all of the terms and subtract out the first n terms, then what I get is the n plus first term plus all the terms after that. All right? So this is this remainder that we're talking about. It's a sub n plus 1 and higher. All right? So we're going to get a handle on what this sum is. So I guess I can fit this in this video. I'm always worried about time. So let's say we look at not just our function that we've been talking about, 1 over n squared, but really any f of x that is positive, continuous, and decreasing. It does have to make sense that it would decrease asymptotically, because if it just drops straight to 0, then you really just have a finite sum. So then the matter becomes trivial. All right. So let's look at a right Riemann sum on that. So if we go to the point n on the x-axis, n being the number of terms I'm summing up, then the next whole number over is n plus 1, and I'm going to build a right Riemann sum starting with that n plus 1 and n plus 2 and n plus 3. Right? So since the delta x's are all 1 and the f of x is equal to a sub n, right? F of x equals f of n, I guess I should say, is equal to a sub n. So this height is always a sub n, the delta x is always 1, so this value of this is going to be a sub n plus 1 since we're using this side. This rectangle, the area is going to be a sub n plus 2, this rectangle could be a sub n plus 3, and so on. So in fact, what you pretty clearly see from here, again, just by comparing areas, since the integral is going to the Riemann sum underestimates the true area, is the way to say that. All right. So what that means is that the a sub n plus 1 plus a sub n plus 2 plus a sub n plus 3, etc., we can geometrically see is less than the integral from n to infinity of f of x dx, using x now because we're integrating a continuous function. Yeah, so this essentially is it. So this is telling you that for a positive continuous decreasing function that matches the terms of the sequence of a series, the remainder that you get from using only finitely many terms of the series is less than the integral from n to infinity of f of x dx. All right, so this is something called the remainder estimate for the integral test. It is found in your Stewart-Kokoska in section 9.3 still, page 680. It's right, it's a little hard to fit this under remainder estimate for the integral test. All right, there you go. So, so this general result, and there's actually more to it than that, so which we'll look at next. So this first result, we'll just start using this first, just to point out that that is in Stewart-Kokoska, section 9.3, page 680, if you want to look that up and read more about it. And once again, I highly encourage you to read this entire section. It's a very readable book, and you will learn a lot that way.